So, can we start? Or we are waiting for someone? 10 people, where are you? Somewhere. They are somewhere. Let's go. Yeah, here's my blackboard. Here's my chat. Here's my something. Come on. Spend some time for theory of signals. So, what I got for today? Remember I told this course is power engineering, correct? For today I have another idea more related to power engineering. It's a second part of harmonic flow in power networks, and at this moment I would like to tackle transformers. power transformers. Transformers are important because it's a transformer application is a good way to change voltage without losing much power. And why we need to change voltage? Because it's a game of transfer capability. The higher voltage, the higher will be network transfer capability. In general, for high voltage network, transfer capability is voltage squared divided by link reactive resistance. And transfer characteristic is AQ generator on the one side, AQ on the other side, divided by sum of reactance and multiplied by sine of delta angle. But it's not the today question, the transfer capability. We only it is much more, let's say, profitable to generate, for example, 6, 12, 14.8, 24 kilovolts, then rise up to multiple kilovolts starting from small 110 and ending at something like 1.25 megavolts. Send your power closer to customer, then it will be distribution network 10, 11, 12, 24, 35 kilovolts. First reduction and second reduction to 0.4 kilovolts to the end customer. Transformer is a good, very good device to change voltage without losing much power. So here, where am I? Where am I? And why this small network is here? This small network is a transformer. It has steel core. Why? Bigger transformer. This. It has steel core because we need a good magnetic conductivity. Good conductivity, good energy concentration. Good energy concentration, less loss. Here is the winding. I have small resistor there, and it's powered from an AC source. I took this voltage. It's a primary current multiplied by some factor, and I will use it in two ways. Guys, this is signal number 1. For signal number 2, let's say it's a second resistor, it's R1, R2, and capacitance. I took capacitance, so R2 it's much, and 1 again omega. Ground, and this is my signal 2. This is signal 1. Also, voltage from, I have two secondary coils. This voltage goes as a blue line to my large scope. Yellow line is the first one. So here, yellow line is signal number 1. This is, let's say, signal number 3. Or secondary voltage. I can mark it with the blue. But what about this one? What do we know about capacitor's voltage? Capacitor voltage is time it's a sum of all charges accepted by capacitor, yeah? Or I should integrate capacitor current in time. Because this resistance is deliberately high, actually capacitor's current is approximately pure EMF of this winding number 2. Now question from the physics. And what is EMF? If this, let's say, has a number of tone V2 and this one. What's EMF of course? Physics. It will be number of turns, first derivative of flux. Agree? And if signal is an integral of E2, what will be the signal to? Integrating derivative. If I take if I do integrate what will I get? Flux with some factor. Or what's the difference between flux and induction? Only the area of core, yeah? At first. If we ignore magnetic if we ignore part, okay, at first, so signal 2 is some scale factor multiplied by induction, yeah? Yeah. I took them to the research figure. I have nice research figure. The here is S1 primary current, yeah? And at vertical I have S2. It's, let's say, K2 induction and S1 resistance, number of turn, space, what? Magnetic force. My research figure will be what? If I would like to draw a chart in coordinate is B, H. What we will get? Mod not good. I should get something like whoop. Something like this. What's the name of such curve? Huh? Oh, you never heard about it? Ah. Can I please get another planet? You never heard about ferromagnetics magnetizing loop? For ferromagnetic material, what can they are magnetized, but they have remained coexertive force. H or primary current multiplied by induction of flux. Material with magnetic, let's say memory, remaining. This one is coexertive force or H0. They are magnetizable. I thought it's in physics course. And should be once more in circuits theory. Oh, you don't have circuits theory. Materials like steel, ferrite, and so on, metal. If you analyze how they react to magnet, when you try to magnetize them, you will get something like this. It's a loop of hysteresis. Up, down. Where is my... this one. That's how it works for my transformer. It's a magnetizing loop of good quality transformer steel. Here, what do I get? This one is secondary voltage. Primary voltage is near sign. Here on the small scope, it's induction or flux. It's a flux channel. What do we see? Voltage near sign. Oh, it's harmonic, yeah? And what about flux? Also looks harmonic, yeah? What about this one? It's a primary current. See, spectrum. Red line is a spectrum of yellow. 1 second, I need... Okay, come here. First line, come on, 50 Hertz. Second line, 150. And here small, 250. Third harmonic. It contains mostly third harmonic. growth is not linear. You see what happens? It's called saturation. On a small, let's say, on small induction, presence of third harmonic is relatively low. On a high, see this deformation. I'm deep into saturation. I will not burn. You can see flux still harmonic. Primary current not harmonic. Why? Why primary current? One important thing with steel core transformers. I need to draw it. This will be time. Okay, this will be here. Here my magnetization chart. Okay, something like this. So this is H or I1 by winding. Here will be induction with some factor. Let's start from the simple idea. I have connected transformer, unloaded transformer to the network. Network voltage, let's say this is network voltage, sine omega t. Yeah. So Y is one primary voltage. What happens? Transformer. Transformer. This is primary voltage. I connected it to the network. What happens next? Some current flow, yeah? And this core magnetizes. When core magnetizes, what we see? What change in flux? When flux changes, what about induction? Self inductance voltage arise. If we are in stationary mode, this is A1 self-inductance EMF of this voltage. Okay, I imagine I have connected. And it's absolutely equal to the primary voltage. It should be equal. They are in equilibrium. Now question, very simple. This EMF is induced by some flux. Yeah? What should be flux to get sine kind of EMF? Cosine? like cosine of omega. This one is flux or induction in space with some vector, with some scale. Okay, now I can do bit of magic. What can I do? I can draw timeline down for what? I will draw a primary current. I'll take, let's say, this is time moment number 1. Here is moment number 1. From the moment number 1, this is point. Here is point number 1. Let's say I take, this will be my time point number 2. This way. This way. This is point number 2. I'm going this way. This is point. Okay, for 0 this is point 1. This is point 2. Let's take, for example, why nobody protesting? What I'm doing? Which way goes this line? Down. I should take this point, not this. If line goes down. Next one. Let's say here, point 3. Here is my point 3. Go this way, this way, this way. Here, the same time 3. Next one, for example, this one. Here, the T. Here is my point 4. And so on. You see how I'm creating? That's how I voltage, harmonic, EMF, harmonic, induction, cosine, again harmonic. But because ferromagnetics do have saturation, current will be not harmonic because this non-linearity. When I go up, I will get something like this. Because I'm going deep into this, how to say, horn of characteristic. For my transformer, yellow line is a primary current. Look how it changed. See? See what happens when I'm deep into the saturation. We can, where are you? No. Where is my, oh, here it is. I can add to my secondary winding. Unloaded transformer. Small load. I'm increasing. Wait 1 second. I will switch for my online viewers. Here, I'm increasing load. Look what happens with magnetizing current. downward, smallward, higher, 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 higher. Up at the short circuit. At the short circuit, induction is half approximately of no load. It's a short circuit regime. Very nice. Okay. I may return to the no load. Nice, nice, nice. So at this moment, what can we tell? Supply voltage, sine, induction, cosine, secondary voltage, sine, everything. But current is not harmonic, current contains third harmonic. And now question, what will happen if I remove third harmonic from the primary current? What if I make this to be a sine? How can I do it? Very tricky question. I made this is resonance circuit for 150 Hertz. It will increase resistance at a third harmonic frequency approximately 4 times. Let's try. I need to buy. Okay, let's do it. Can you see? Now, primary current is harmonic because I cut 150 component. Oh, okay, it's near. See how deep I reduced 150 Hertz component. But what about flux? You see what happens with flux? Can you see? Is it harmonic? No. Flux I can draw a torsion. Becomes something like this. Can you see? Can you see?
The flux?
Yeah, flux.
Mm-hmm.
And what's the result with the voltage? See what happens? Without voltage is silent. If I add filter, see what happens? Voltage is distorted. Voltage amplitude becomes higher. Primary current sine, flux. No, this is not sine. And what happened with voltage? Why? Maybe you can tell us why? Your Facebook can help us. Why removing of third harmonic causes voltage distortion? Tell us.
Who?
You. You definitely should know answer. Or you are artificial or intelligent on the other side of your palm. Someone should know answer. Why voltage? Why removal of 150 Hz component makes primary current nicer, but cause distortion of the secondary voltage? Of course you don't know. After I remove this 150 Hz component from the primary current, nothing compensates nonlinearity of steel. If it would be an air transformer, air transformers do exist. Where is my air transformer? Why is they calling me? Yeah, но это уже после лекции. 16:05. Я вам скину эту таблицу. This is air transformer. It's no problem with linearity. Problem is with efficiency. It's very ineffective because it has high magnetic resistance. This transformer much more effective, but it's a steel core. And when you do something with ferromagnetics, they all are non-linear. They all have this loop of magnetizing. Nothing is ideal. At the moment where I cut third harmonic from magnetizing current, I had a flux like cosine omega. It was original flux. Removing third harmonic, it's like adding flux component with this one is 50 Hertz. I'm adding with the minus sign something like it should go up, down, up, down, and again. Something like this. This is 150 Hertz. It's a component of flux pushing here. See what happened with flux? It's like wider and lower. I can make it bigger. See? Distorted. In case of uh, 50 Hertz non-distorted. See? What? Can you see the flux? Oh, for a moment. Oh. I remove this, how to say, I cut mountain top, and it can be assumed as an addition of minus 150% flux. I will have my secondary voltage is a derivative of this signal. And this derivative of cosine is sine. It's okay. Derivative of distorted cosine, here it is blue line. Now you would ask a question. What an idiot should put filter to remove third harmonic from the magnetizing current? Why? Of course, no one say would deliver distort the voltage. Yeah? Yes. But no. My tiny friend, three-phase transformer. Oh, here. Single-phase network is one. But what about polyphase network? I can draw three transformers. No. I will draw three small transformers. Number 1, number 2, and number 3. And I will connect them A, B, C in 3 off ground. Possible this will be 10 kilovolts side. And or 11. Ground. A, B, C. Okay, let it be grounded. Three-phase network. What's the nominal voltage of distribution network in your country? 10, 12, 11.
kV, right?
Kilovolts, yeah, kilovolts.
33.
3?
3 kV.
Oh, 3.3 it's a single level, or you have 24 above?
The nominal one?
Because 3.3 is too small for complete network. Maybe you have two idea when you have 3 for local and 24 or 27 or something like this for high.
Well, low would be like 11 kV.
3.3, 11, and high 24, 27.
No, 33. 3.
Only. And grounded or isolated neighbor. Grounded, because you have this nice power transformers.
Yeah.
American system. Okay. So it's your case. Each housing has its own. Here we have 3.3 kilovolt line to line, grounded net. How 150 hertz component will flow? Here, 50 hertz. We will have nice A, B, C star, and sum of them, if we sum this vector, current, if we take a current here, at 50 hertz, it should be 0. if we have equal transformers somewhere. Each polar has its own nice transformer, but let's assume they are equal. And what about 150? What about third harmonic? 50 hertz. Or 50, or you have 60 hertz.
No, 50.
50. So it will be 150. What we will see? For 50 hertz, for 150, what? It's a zero sequence, A, B, C. We will see triple current. Here, we will see triple 150 hertz. I need to show it. Yeah? You don't believe me? It's very strange. Here is my little helper. It's a programmable three-phase source. I can simulate three-phase network. Of course, I can connect real network for here. Actually, it's because I have reduced voltage there. Okay, let's see what. Let's see what will happen. Let's see. First, I need a secondary voltage. Where can I get secondary voltage? Secondary voltage and 1 second, everything should be connected. This will be neutral current. Zero, switch off, switch off. I can switch this off on 2. One moment, we'll get something. Or not. It's glow or glow. Stop checking peripherals. Give me. Yeah, ready. Ready. Oh. Let's see what can I do. Okay, I will put 3 voltage, each 200 ohms. see it? Yeah. Yellow line is a secondary voltage, and blue line, neutral current. Blue line, I took the, so I have yellow. This is my first signal, and here I have sensor, it's my second signal. Do you see frequency? See what happens? Transformer is symmetrically loaded. Ionized group of 3 single-phase transformers. From each one flows 2 components, 50 Hz and 150. Sum of 50 Hz components is 0. Sum of 150 Hz component will be triple. You see? It's 150. What will happen if I disconnect this wire? It's a ground wire, it's not dangerous. What will happen if I disconnect? Oh. What will happen if I disconnect the switch?
Only on this other side?
Yeah, only on earthing. On earthing side. For if we have symmetrical load, for 50 Hz, it changed nothing, because sum anyway is 0. But for 150, it can no longer flow. We will see in reality the same situation, the same idea what I artificially created with the circuit. If first, at this moment, this transformer is for 230 volts. Now I have only 200 volts. Look what happened when I disconnect. Small change in amplitude. Why? Because relative weight of third harmonic is low. 1 second. I will put it to nominal voltage. 230, 230 and 230. Nominal voltage. I added 30 volts. You see increase in third harmonic. And disconnection. Now it's more visible, isn't it? And what about for the short time? 250. 250 and 250. Not increase. And see what happened. Now influence is more than visible. This is tricky thing. At day, you have loaded network and voltage at lower permittable. Change is because we are not in this saturation point, relative weight of third harmonic is 7, 8, 9%, something not so heavy. At night, load decreases, voltage goes up, and we go deep into the saturation zone. See the difference? Sorry. Come on. When you start? 250 volts. How many? Stop. And 1 second, I will go back to 230. See the difference in, I only changed 20 volts. Now voltage 230 was 250. But because I'm not in saturation zone, you see the difference in third harmony. It's a relative double. And influence. Here I disconnect neutral wire. 0.4, something like this in amplitude. Daytime, when load is high, influence of the effect of the third harmonic is relatively low. At night, voltage rises, we go deeper into the saturation zone, and effect of the third harmonic become very serious. Again, for comparison. 240. I'm adding only 10 volts. See the difference in harmonics weight. And change in secondary voltage. At night, disconnected neutral wire causes overvoltage and burn of electronics equipment. Daytime, everything fine. No one, the problem with disconnected neutral can remain, say, undetected many days until voltage rises a bit, some 10% increase, and you're done. Okay, it's fine, but what to do if we have an isolated neutral distribution network? Really, in local standards, transformers with rated power up to 1.5 megavolt amps are permitted to operate in star grounded star connection, not higher, because of voltage distortion. If I need more. One moment, I would like to show one more trick. One more thing about third harmonic on this. Your transformer. one moment. But when we take free wave transformer, because it's cheaper, there is one additional moment. What kind of moment? In case of free separate transformer, 150 Hz component can easily circulate in their cores. Nothing on its way. Here, in this part, sum at 50 Hz will be 0. Yeah? Sum of flux. For 150, flux free, they are equal in A, B, C leg. It's 150. This was 50 Hz. Sum is triple. In such transformers, this flux should go by air. See what I got? A link. Fourth leg. My transformer is free leg transformer. $240 volts, secondary voltage, neutral current. Check voltage. I'm adding the path for the zero sequence or for the third harmonics. What? It's what is better. When you need to perform, let's say, measurements in such network, transformer 1, 2, 3 leg. 1, 2, 3, and instantly leg number 4. Additional leg for zero sequence. For medical equipment, often used so-called armored or shield transformers, 3 main cores and 1 more side on the sides. Okay, what I like to draw, one idea. Oh, here is my large transformer. One winding, 2 winding, 3 winding. Let's say A, B, C phase. Okay, what I'm 1, 2, no, 1, 2, 3. Oh, this one is nice. Oh, yeah. I draw a transformer with delta connection. They do exist. Delta connected transformer. No. One, two, three, B2. A, C to B, and yeah, this way. Delta connected transformer. Can I connect transformer in delta? Why not? On the secondary side, we will have star connection with grounded center. And what about primary delta? For the 50 Hertz, there will be no circulating current because sum of 1, 2, and 3 is 0. And what about 150? For 150 Hertz for third harmonic, sum will be triple. And we will see what? This delta is like short circuit for the 150 Hertz. This means what in every core we will see two opposite flux. One for magnetizing, because network is isolated. At first moment, 150 Hertz, a third harmonic component of the magnetizing current, cannot flow and appears what there should be a third harmonic or 150 Hertz component in the flux. But third harmonic in the flux induces 150 Hertz current in the delta. It circulates and produces 150 or third harmonic flux directed against demagnetizing core. For such transformer, there will be no distortion in voltages. So if you need good voltage and your network, distribution network, is isolated neutral network, okay, no problem, just connect your transformer, not star, but delta star. And everything will be fine. All these transformers, they are tricky. Yeah? Transformers. So, conclusion. If we have a steel core transformer to receive harmonic voltage at the output, flux should be harmonic, but because of non-linearity of steel core, magnetized current will contain third harmonic, will be non-harmonic. If there will be any obstacle on the flow of this third harmonic, secondary voltage will be distorted, and we will possible get problems. For polyphase network, delta connection solves problem even for isolated neutral networks. I think maybe you have some questions. I think we can make a break. We have second hour today. Yeah, and it will be rectifiers. No one connected online. Maybe someone